One of the other skills we're going to need to develop is the ability to translate equations from polar form to Cartesian form. Now, what does that mean? When we say we have a Cartesian equation, we mean we typically have something like y equals x squared, something like this, where the variables are x's and y's. And the goal would be to try to end up with an equation that just has r and theta in it, and we don't know what this is going to look like just yet. But the general process is basically just algebra. Here we have some substitutions that we can make, and our goal is to make the substitutions so that we end up with the appropriate variables. So if we start with something in x's and y's, our goal is to end up with r's and thetas. If we start with something in r's and thetas, and we're trying to get to x's and y's. And everything will be a matter of making the right substitutions and doing the correct algebra. Now, even though these are the forms of the equations, there's one other form of this, r squared equals x squared plus y squared. This form is also useful in doing these conversions. And basically, that's just this one being squared, or it's a representation of the Pythagorean identity when you actually substitute these in. So this is going to be useful for us when we do our examples. So here's an example. Convert x minus 2 quantity squared plus y squared equals 4 to polar coordinates. So we have a formula in Cartesian coordinates. We have x's and y's, and our goal is to turn it into r's and thetas. So when you have one of these, this direction, typically you just look for the x's and y's and you make the substitution, and then you do some algebra to see how it simplifies. So let's take a look. Our two substitutions, x equals r cosine theta and y equals r sine theta, can just be dropped straight into this equation. So r cosine theta minus 2 quantity squared plus r sine theta squared equals 4. Now we have to do a little bit of substitution and see what happens. So let's see what we can do with this. We're going to have to FOIL this out. So this is going to be r squared cosine squared theta minus 2ab. So 2 times 2 is 4. 4r cosine of theta plus 4, and then this is plus r squared sine squared theta is equal to 4. Once we get to this point, we have to let our algebra instincts take over. We have a 4 and a 4 here, so we can subtract 4 from both sides, and those will cancel out. And let's move these two terms together. R squared cosine squared theta plus r squared sine squared theta minus 4r cosine theta is equal to 4. Oops, equals 0. The 4 is canceled out. Right. Okay, well, let's see what we can do. When you look at this, something should jump out at you about it, which is that you can factor out an r squared. R squared cosine squared theta plus sine squared theta. And we can move this to the right-hand side of the equation. Equals 4r cosine theta. Sine squared theta plus cosine squared theta, again, your instincts need to take over. You've seen this pattern before. This is equal to 1 because this is the Pythagorean identity. So we have r squared equals 4r cosine of theta. Now at this point, you can leave it like this. This is technically correct. There's actually two formulas that we get out of this, and this set of points will satisfy, will satisfy at least one of them. And so you either get r is equal to 0, or r is equal to 4 cosine theta. Now, strictly speaking, you would have to move this over, factor out the r, and use the zero product property to see this. Or you can, with experience, you can just jump to it straight here. Now, here's the interesting thing about this. R equals 0 is just a single point, and r equals 4 cosine theta gives us many more points. And so when we set this up, we're actually setting ourselves up with two different cases, and this case is actually a subcase of that one. So when theta is equal to, for example, pi over 2, then this is equal to 0, and so we get this point is included. So this is extraneous here, but it's worth at least writing it out. In some higher levels, we may have to deal with multiple possibilities separately, but in this case, we can just leave it like this and take this one because that's a subcase of that one. And so this formula right here can be written like this. Now, what's interesting about this is that we should be able to recognize this shape. If you think about it, x minus 2 squared plus y squared equals 4. That's a circle of radius 2 centered at the point 2, 0. So here's the point 2, 0, a circle of radius 2. So this formula right here is actually the polar coordinate formula for a circle centered at that particular point. So here's an example in the other direction. Convert r equals 3 over 1 plus 2 cosine theta from polar coordinates to Cartesian coordinates. Now you could start from the very beginning and substitute r equals the square root of x squared plus y squared and try to do all the manipulations from here. It'll work, but it'll just be a little bit messy. Instead, it's easier to take this thing and try to simplify the parts that we can first before substituting in the more complicated substitutions. So let's take a look. Draw a line here. R equals 3 over 1 minus 2 cosine theta. So what's that going to do for us? Well, first thing that we might see is that it would help to clear the denominator. So we start with R equals 3 over 1 minus 2 cosine of theta. And we multiply both sides by the 1 minus 2 cosine theta to get R times 1 minus 2 cosine theta is equal to 3. And now when we distribute, we get R minus 2R cosine theta is equal to 3. And here's where what I mean by that substitution making things simpler, because now we have R minus 2 times X is equal to 3. And so R is equal to 2X plus 3. This form right here is much easier to work with than having square roots and a fraction floating around. Once we get to this, we still need to replace the R because we really need the R to be in terms of X's and Y's. But rather than substituting the square root term, it's often easier to use R squared is equal to X squared plus Y squared. And so we take this, we can square both sides of the equation. R squared is equal to 2X plus 3 squared, like this. Because now what we get is we get X squared plus Y squared is equal to 2X plus 3 squared. Now there's more you can do. You could actually try to write this into a certain standard form or whatever, but this is good enough for me. For this class, this form right here, where we have X's and Y's in a fairly reasonable representation, there's no excess square roots or anything like that, this would be an appropriate place to stop for this one.